Welcome to third video of TSAP review, Traffic Safety Analysis Procedure Manual, released by TxDOT. In this video, we will be looking at chapter 2, data collection. I believe this would take us 2 videos to complete chapter 2, and we'll see how it goes. So data collection. Data collection is an important part of traffic analysis. If we do not have a good data, then there is a term which is frequently used called garbage in, garbage out. You may have heard about it. Garbage in, garbage out is what this slang tries to say is, if we do not have good data, no matter how good our methodology and everything else is, we are not gonna get good results. So it's very important to collect good data, make sure the data is consistent, data makes sense, and to make sure data is of high quality. So the first paragraph, the first part is introduction. I just going through the needs of having a good data source. The second one is type of data which we collect. So there are different type of data we collect for traffic analysis and safety analysis. So some of the common types are, first one is geometric data. Geometric data is related to physical characteristics of a roadway. And below are the list of data which we collect. First one is geographic coordinates. So if we are looking at ramp locations or crashes, then we try to collect geographic coordinates. Those are in NAD 83. NAD is North American datum. Is North American datum. Most of the GIS files, Geographic Information System files we work with, comes with NAD 83. The number of lanes on arterial, freeway, multi-lane highway. Lane assignment. So lane assignment is, let's say we have an intersection. Lane assignment is simply this lane is left turn only, this one is through, this one is through and shared right. Let's say this one is through and left shared, and this one is through and right shared. So getting this information on which lane is assigned to which moment is called lane assignment. Lane assignment. Then we have lanes, shoulder and crosswalk width. So first we want to know whether it's lane width. Typical lane width on freeway, one number to remember is 12 feet. A shoulder width for typical shoulder width for freeway to remember is 6 feet. And crosswalk width. Shoulders are after when the last lane ends, and usually there is a shoulder provided. Sometimes it's 6 feet, sometimes it's 10 feet. Then we have crosswalk width. So this is crosswalk length, crossing the intersection, and maybe we are interested in crosswalk this width as well. So I believe this crosswalk width is referring to the length of the crosswalk. Presence of sidewalk or pedestrian elements. So if we are working with intersections, then we definitely need to know whether there are sidewalks or pedestrian elements, and typically they are present. So when we are working with intersections and controllers, we need to know that these elements, and they dictates our signal timings and intersection design. Then we have length of turn base. So this is an kind of little bit ambiguous, and we will discuss in one of our videos. Length of turn bay. So if we have turn bay which is tapered like this, let's say we have more lanes, then length of turn bay, and the marking usually goes like solid line till here. So now there are various options to calculate this length of turnway. One is from here to here, where the solid marking is there. Then another option is to go from here to this taper. Then from another option is to go up to the end of taper, and another options are to go in between. So for traffic analysis, like we have discussed in one of our videos, for freeways, the length of acceleration or deceleration lane, when we are looking at acceleration or deceleration lane, I'll change the color. Then we start from the merge, like the gore point, and go up to the end. So based on highway capacity manual guidelines, and if you are working on freeways, then this is where we will measure to the end here. However, when we are working on synchro analysis, we measure up to a point where the vehicle can physically fit in. So it's not till here, many engineers measure it till here, many engineers measure it till here, few engineers measure it till here. Ideally, for synchro analysis and other, when we are looking for something called storage length, when we are looking for storage length within synchro, then we should be measuring I think based on experience, we measure it till where the vehicle can physically fit in, because if we try to fit the next vehicle in, then it's gonna end up in the next lane. So if we think the vehicle is gonna fit in till here, then we will measure it till here. Let's say we have a case with a pretty long taper. So if we have a case, usually some of the tapers are very long as well, and let's say we have a roadway like this, then we will measure it till wherever we can think the vehicle would fit in or physically fit in. So the length of turnway or the storage length for the calculation of traffic analysis is till from the stop bar to here. The length of this turnway definition changes for design perspective. So this is for traffic analysis. However, when we are trying to follow the TxDOT RDM, TxDOT Roadway Design Manual, then the length of turnway has a different definition. Within the typical roadway design manual, I'm drawing a horizontal lane. So let's say this is our taper, and this one is a dotted line. Then from the stop bar, this length is called total storage in terms of roadway design manual. So it goes up to the end of the taper. Then the taper is measured separately. So there are requirements on the taper and there are requirements on the total storage. The total storage is combination of storage, which goes up to here, which is designed for storage, and this part is designed for deceleration. Okay, next one is ramp spacing. Ramp spacing is typically what is needed in highway capacity software, but we do not collect it. There are better way of figuring out ramp spacing. Let me reload this page. So ramp spacing, we typically do not have to go and collect it in the field. There are better way of handling ramp spacing. The first one of the better ways is to draw the segments on the map and have the map automatically calculates the length. If we want to calculate ramp spacing based on Google Earth imagery or proposed schematics. So when we are trying to calculate the ramp spacing from Google Earth, specifically for analysis in highway capacity software, that's the major use of ramp spacing. Otherwise, in VSIM and other software, we simply draw the geometry and the software already knows how long the spacing and lengths are. However, when we are dealing with spreadsheet calculation or highway capacity software, Then we need to input this ramp spacing. However, there are smarter way of doing things, which are just drawing it on a map and let the automation or some other feature calculate the ramp spacing for you. So this is an input in highway capacity software. However, we do not go and gather this data. We can automate this very fast. So we get the ramp spacing through automation. And the ramp spacing is not an output. So the way it works is we have Google Maps. In past, from Google Maps we get ramp spacing, or recently Bing Map is used a lot, so I will mention Bing Map here because Bing Map is available in most of the software, and Google Map and Google Earth are available outside. So from them we get the ramp spacing, we feed it to SCS and plus other Excel based tools, and then we get the results. However, what we are doing is we are moving from Google Map without calculating ramp spacing, or indirectly having this information, feeding it directly to SCL into Excel without actually writing them down. We just take these maps, do some automation, or we do some tricks and then move it to SCS without actually have to compile this data and get the results. Clear zone is something that is kind of we get it either through Google Earth imagery or from the schematics. Curvature of the roadway, that is center line alignment. So when we are looking for roadway curvature, let's say horizontal curve, then the radius for the inner lane is different than the radius from the outer lane. So when we refer to a roadway radius, we refer to the center line. Grade, which is the vertical grade, and this is again a good information. Many times we in the absence of grade information, we assume the freeway to be rolling terrain, or sometimes some engineers use level terrain. But if the grade information is available, then we can use it and we can ask for it. Many times the grade information is not available. Median width, we can get it from Google image. Median type, there are three different types. One is divided, undivided, and barrier. Even in undivided, there can be barriers depending on the type of barrier. It may act as a divided or undivided. So there are different kind of barriers, and based on these barriers the safety analysis changes. So median type and the barrier type has a very significant influence on safety analysis and safety. So it's an important parameter to have, because a vehicle, if it's a divided by, let's say, a concrete block, and a vehicle hits head on the concrete block, then the crash may be severe. So not only the median type, which is divided and undivided, is also important to get the type of the barrier that has a significant impact on the crash severity and manner of collision or crashes in general. So barrier type has a significant impact on crash severity, which we have discussed in one of the videos. Please refer to chapter 4 of the video series we have for more details. Let's go down. Then we have the right of way. Right of way line is usually given in CAD and it comes with the survey file. So in traffic operations, we do not need to calculate CAD right of way. Is usually done by roadway team, or roadway team gives us a CAD file which has a right of way, usually in pink color. Driveway entries and locations from Google Map. Again, we don't need to gather this data, we just need to kind of look at Google Maps and see, okay, there is a driveway. Location of railroad crossing is an important one. If there are railroad crossing in the project we are working, then we have to take care of railroad preemptions. Railroad preemption in traffic operations, and there is a form we will discuss, which we need to fill out for railroad preemptions to ensure that we are giving enough time, and the phasing is set in a way that we are fulfilling the railroad requirements. So I just scroll down and we're discussing railroad, and I noticed there is railroad preemption on the next page. If we are wondering on which page number we are in the text, we are at chapter 2, page 1, and we can also see the PDF page number on top left part of screen here. For railroad crossing, which plays an important role in traffic operation, especially signal design, there is a form, TxDOT form 2304, I believe. Let me have a look real quick. Yeah, 2304, which goes through the calculations of different geometric calculation and signal timing calculations that ensures that the railroad crossing is safe. So there are different railroad crossing signals and the gate arm. So this depends on geometry of intersection, speed of approaching train, type of detection of the train, and several timing parameters. So we want to ensure in timing parameters, the most important one which plays a bigger role in railroad preemption is the pedestrian timings. For most of the timing, we can reduce the green time or the yellow and other times. However, when there are pedestrian crossing involved in the railroad preemptions, then it's very difficult to reduce the pedestrian timings. And there are certain guidelines on how to reduce the pedestrian timing within the form 2304. However, the biggest consideration in terms of timings for the railroad preemption is the pedestrian timings, because that accounts for the large time that is needed for, it's called transfer of right of way. There are two different railroad, UPPR, and there is one more, and based on the type of railroad, the right of APT, advanced preemption timing, I think there are requirements, needs to be less than 50 seconds, or the total time needs to be 50 seconds. So APT needs to be between 20 to 20, less than 20 to 25, based on the type of railroad crossing. So there are different, for UPPR I believe is less than 25 seconds, and for the other one is less than 20 seconds, which is very difficult to meet when we have pedestrian crossings. So just some things which flash in my mind while we are looking at the railroads. We will discuss this more in one of our videos in greater detail about the railroad crossings. So geometric data can be gathered using TxDOT online data portal. TxDOT has this GIS portal. We can Google search TxDOT open data portal, and this is a GIS portal where we can download the data in either GIS format or CSV format, and KMZ format, KML format. So we can download CSV file, we can download GIS files, we can download KMZ or KML file. the entire databases. So some frequently downloaded data are roadway inventory, which gives the attributes related to the roadway within the state of Texas. Then we have the ADD data. Although we can get the ADD data from STARS 2 and statewide planning map, getting it from GIS portal allows us to import a large volume of data without actually just looking at the portal and manually writing it. So ADD data, if we are looking for large volume use, then we can download ADD data. Another data we download from this portal is district and county maps, or we can say geographical boundaries. So district and county maps. The next one is Google Earth, which we frequently use in almost all the projects. Google Maps, Bing Map. Bing Map is now being more used in software such as Vissim Synchro and SCS. So most of the softwares comes with Bing Map now. Vissim, Synchro, and nowadays SCS, and it helps us to input the geometry faster in all three softwares. Survey files. For schematic project, a survey is conducted from the roadway team. So survey files we typically get from survey by roadway team, and we get the file in topographic survey, topographic layer, also commonly known as topo. As-built are the plan which are after the construction is done. So let's say we provide PSNE package, project specification and estimate, which has all the fine details on how roadway needs to be there. However, if there are some changes to PSNE during construction, those changes are marked and updated, and those are called as-built. As-built is kind of showing how the roadway is getting built when the construction is happening. So as-built gives us a good indication and is a good data source to see how the roadway looks like. And the other online resources. However, it is recommended that a field visit be performed when possible to verify the existing geometric conditions data gathered digitally. So a field visit, there are several recommendations in this manual. One of them is field visit, which is a good thing to do. So I'm a big fan of field visits because I believe when we are working on project, it gives a better idea about the conditions when we visit in the field rather than just looking at maps. However, because of budget constraints, even though it's a great idea and it's beneficial, it takes let's say to prepare for the field visit, to go out in field, and if there are two people, let's say it takes between 8 hours to 16 hours in the field, and it does cost money to get the engineers in field. So for majority of project the field visits, so this is during field visits, then there will be some post processing and report writing. Majority of project field visit is not conducted. I would say 90% of project we rely on Google Earth and other information because of budget constraints. Now this can easily be between 5,000 to 10,000, or I would say 2,000, 5,000 to 10,000. Field visit can cost us between 5,000 to 10,000 US dollars, and usually because of budget constraints and many other constraints, field visit is not done in 90% of project. We do field visits when the imagery on Google Earth is outdated, or when the imagery on Google Earth is less than 3 years old. So Yeah, just some generic things, that there are a lot of recommendation doesn't mean they actually do happen in reality. There are a lot of recommendation, and given that more budget, an engineer can do many things. However, usually the budgets are limited, and we are always pushed a little bit in some sense to reduce the budget on all the projects, on especially the subsequent projects. So a lot of good recommendations are there, but those are more of theoretical things than practical things. Traffic operational data. Traffic operation data is based on traffic control devices and roadway characteristics. Other than roadway geometry, below is the list of general traffic operation data that is needed to perform the traffic analysis. I'll reload this place to clean things up. So first one is speed limit. Speed limit is an important operational data that we need. So speed limit, we can gather speed limit from Google Earth. That's our best source. Sometimes if we are working on a large region, then we also can get speed limit from TxDOT statewide planning map. Statewide, however, it is known to have inaccuracies within the planning map. So even though we can gather this data, we do go and verify this. The smaller the street, the more chances of the data being wrong. For example, freeway may be better coded than arterials. And in general, the accuracy of the statewide planning map for speed limit is limited. However, if we are working on a larger region, it can act as a visual check on the data we are collecting. Operating speed is barely calculated in the field, is the 85th percentile speed. They are only done for few speed studies where there are safety concerns. However, in majority of projects, even though highway capacity manual, and there are many manuals that has the term operating speed or the roadway speed, which is 85th percentile speed, we do not go and actively calculate it. We estimate it based on speed limits, and then design speed given by our roadway team. Then we have traffic control type and locations from Google Earth. A traffic signal timing plan, we request it to our TxDOT PM. If we get lucky, we get it in a Excel format with phasing. Excel format has phasing which we can use. However, this is only like 5% of cases. In majority of cases, TxDOT PM sends a technician to the signal controller. Let's say this is a signal controller to have what is called long readout. This has all the controller parameters. This is controller readout, which has all the parameters that are related to signals, detector, schedule. It's usually like 1,000 lines long, and is a .txt file for most of the cases. And we try to estimate the signal timing based on the controller readout. The two information that is missing from the readouts are phasing diagram, which we typically estimate based on our experience and knowledge about the typical controllers. And another important information that we do not get is the detector layouts, or even the assignments. So again, we have to make some assumptions based on our knowledge and experience. So detector layout and assignments. But these two information are needed for traffic operations. So we get almost all the information from the controller layout except these two, which are almost needed for all the projects we work on. Driveway spacing and location, just looking at Google Maps where the driveways are and how they are operating. Parking occupancy. Parking information we generally don't need unless we are working on parking studies. Roadway functional classification, area type, and driver behavior. So roadway functional classification we can get from TxDOT statewide planning map, and usually that's the best source. Area type, rural, urban, and suburban, we can get it either from planning map or for the crash record information system, which has crashes by this. For the purpose of classification, an area is defined as rural if the population is less than 5,000 people. Then it's called small urban, between 5,000 to 50,000. Small urban or suburban, and then suburban or large urban greater than 50,000. Suburban areas are typically just the outer areas of urban areas. So we have rural, small urban, suburban. So we have rural, which is less than 50,000. Then we have small urban. These are small cities, we can think, which is between 5,000 to 50,000. Then we have urban, which is greater than 50,000, or large urban, greater than 50,000. And suburban areas are just the outer areas of the urban areas. Additionally, if we want to divide the segment into rural versus urban for the crash analysis, then we will define an area as a urban if the population is simply greater than 5,000. So anything greater than 5,000, if we are dividing it into two categories, then anything population greater than 5,000 becomes the urban area. And we typically have this information coded within the crash data, so we do not have to figure these things out, but just for the background information. We do not calculate driver behavior, although we should calibrate. These things needs to be done at statewide level by TxDOT, or more specifically TTI. So Texas Transportation Institute collects and kind of maintains all the data, and we can potentially get this data, or this is something not a consultant do. So driver behavior, acceleration rate, deceleration rate, lane changing behavior, car following model, these are out of reach of consultant world. So this would be something institute like Texas Transportation Institute or TxDOT would collect and would provide some default values or range of values for us to use. Lane utilization, like we have discussed previously. So previously we discussed lane assignment. Let's look at lane utilization. So I'll reload this one. Reload one more time. So lane utilization is, let's say we have a through, and we have a through right, and we have a exclusive right turn lane. So let's say we have an exclusive right turn lane and through right. So there may be some right turn vehicles in this one, and then there may be some right turn vehicles and through vehicles in this one. So not all the lanes are equally used by all the vehicles. So we try to gauge how much lane is being used by which moment. So we are looking for lane used by movement. So let's say 80% of right turn vehicles are here, 20% of right turn vehicles are here. Now let's say 40% of through vehicles are here, and 60% of through vehicles are in this lane, assuming this is going through. Then this is called lane utilization data. Lane utilization data is a little bit refined data. We do not go and gather it actively, but if you are working on signal timing projects, then we do collect or do figure out the lane utilization data. So signal timing projects. Next we have railroad preemption and signage type and location, whether it's regulatory sign, warning sign, and guidance signs. Multiple sources of data may be needed to gather all the traffic operation data used to perform traffic operational analysis. Data such as speed limit, intersection control, and roadway classification is available in the field or with online imagery or GIS database or other online sources. Let's move on to the next section we have, which is the most important one out of this data, this chapter. So traffic counts. This is the most important one out of everything within chapter 2 from personal perspective, because this is what we kind of need in majority of project, traffic counts. So now we are going to focus on the most important aspect, traffic counts, which we typically collect in the field. So one of the fundamental data type needed to perform traffic operational analysis is traffic counts, or in more technical world it needs to be traffic volumes, which are estimated based on traffic counts. So the most fundamental thing we need for traffic operation is traffic volumes, which we estimate based on traffic counts. There are several types of counts that may be needed based on level of details. It is recommended that traffic count data be collected on a typical weekday that represents a typical day travel pattern. So this is something that needs some explanation. So typical weekday is something that we have traditionally done. So traditionally we have collected data on typical weekdays for majority of project, and typical weekdays are considered to be Tuesday or Wednesday or Thursdays. Under regular driving conditions, which means no accidents, which is mentioned below here. So to avoid days which are around the holidays or during inclement weather or during crashes, if there are crashes on the roadway, and there are some more on the next page, or during construction or lane closure or during summer break. So a typical or any situation that may present atypical travel patterns such as special events. Also typical weekdays or typical day of data collection traditionally includes when schools are in session. So traditionally, and even right now for majority of project, we try to collect data on Tuesday, Wednesday, Thursday. In the month of February to April, and in the month of September to November end. So these are the month in which we try to collect the data, and this is our typical approach, and which is written here, and it says on which day we should collect data. However, there has been major changes in the way we traditionally approach the traffic counts or the traffic in general. So nowadays there is a term called trip reliability, which is becoming very important and which is mentioned in the manual. However, this guidelines, it seems a little bit inconsistent with some of the further guidelines that is given in the TSAP manual. There is something called trip reliability. Trip reliability is a concept which says how fast reliability and resiliency. So how our performance measure behaves under let's say unusual conditions. So let's say the weather is rainy, then how the travel time changes, or if there are accidents, Then trip reliability and trip resiliency are new terms that are being more used within the FSWA guidelines and highway capacity manual guidelines. Now, for example, let's say Texas was a state, or some part of Texas receives rain for let's say 100 days of an year. Then we cannot design a roadway for dry weather, because for majority of the year is raining. So I disagree with this classification, which has been our typical approach on majority of projects. So this is a typical approach which we use in majority of projects. However, the guidelines are changing and we need to consider the number of days where certain weather are there, when certain accidents, let's say there is a roadway with history of accident that there are like 2 to 5 accidents per day, then we cannot design this roadway without accident on a typical day, because we know that in majority of days there will be accident. So the idea nowadays is to have this 365 days divided into let's say some proportion where is weather type is certain, let's say it's raining, some proportion is snowing, some proportion has accident, or they may be overlapping, and then collect the data. So this approach is called reliability, or cluster, or in micro simulation there is a cluster analysis. That's the basic idea. The basic idea is to move away from the traditional approach which is mentioned here, to collect 2 days of data or more days of data based on typical day, which we have traditionally done. However, if we have a region within the state of Texas where it rains for majority of the year, or if we have a roadway where there are, let's say, a lot of crashes every single day, then we have to design our roadway such that it accounts for those conditions. So if we are working on a project in 2023, I would say we would follow this guideline, but ideally towards, let's say, 5 years down the line, by 2025 to let's say by 2026 and beyond, we would like to move away from these guidelines which looks at typical day, because typical day, it depends on how typical it is. Out of 365 days, if the typical day represents 360 days, I do not have any problem. But out of 365 days, if the typical day represents only 90 days, then it's not a good analysis. So some discussion about the traffic count. This is on which day should we collect the data. So what if we have a rainy conditions for 100 days and dry conditions for remaining 265 days? Then we would collect one data set during rainy, one data set during dry, and try to analyze both. That would be a better approach moving forward in the future from our personal perspective. It is recommended that traffic count be collected for atypical travel pattern based on specific project. For example, if the purpose of projects, so this part discusses sometimes we have to collect atypical traffic patterns. Recently we are working on projects, and there are some special events locations, then we had to collect data for the we had to collect data for weekends. Airports are classic examples of these things, where we collect 7 days of data, and Friday is typically the peak hour day, and Friday evening around 4 to 6 p.m. Next one is turning moment count. Turning moment count, like I mentioned, is not available within TxDOT databases. There are some estimation by certain big data sources, but those estimations are typically very poor. So turning moment counts are generally field collected. Traditionally, we have collected 1 day. Recommendation has always been to collect 2 days of typical weekday data, but in order to save money and budget, many consultants just collect 1 day of data and use 1 day of data, assuming 1 day is similar to 2 days. But the guideline has always been to not the guidelines, but the best practice should have been to collect 2 days of data, which is mentioned here. So turning moment count based on this TSAP manual for Texas project. So based on TSAP manual for Texas project, turning moment count should be collected for 2 days of 2 consecutive weekdays and based on coordination with TxDOT project manager. A typical weekday count is defined as the count occurring on Tuesday, Wednesday, or Thursday. Like I mentioned, it is mentioned a little bit up that count data be collected in 15-minute increment, which is used. Most of our data input is in 50-minute. Data input is in either 15-minute increment, for example VSM, or it's 60 minutes or 1 hour data input, but we do use the peak hour factors, which changes the 60 minutes to kind of peak 15 minutes. So the data needs to be collected in 15 minutes increment. Turning moment count may include vehicular, pedestrian, bicyclist. So whenever we collect data, we have the vehicle data plus pedestrian data. Recommended TMC methods are 15-minute increment, typical weekday, 2 consecutive days, minimum of 2-hour period, which include peak hour. So these are some typical recommendations on when to set up the counts. Counts are expensive. 1 day of traffic count for a project can usually cost between $20,000 to $30,000. So any day of extra count is a big cost. So instead of using 2 days in past, several times in majority of projects, it has been switched to 1 day to save budget on projects. However, I'm happy that this guidelines kind of reinstates that we should be collecting 2 days of data and then average them out rather than just 1 day of data. But the traffic counts are expensive, so it's something to consider. Segment traffic counts are conducted along the roadway during a typical week for consecutive of 7-day period based on coordination with TxDOT project manager and collected in 15-minute increment. The one thing I believe this segment count should include is the main lane and ramps, but based on these guidelines, I'm not that clear. It's very expensive, like I mentioned, to collect the data. So if we are collecting the segment counts for main lanes and ramps, then it will be very expensive. If we are collecting only for main lanes, then we will not be able to get the complete picture. For example, if we have a roadway like this and if we collect data here, we will not be able to know what is happening in between because it will depend on the ramp volume. So I believe the guideline is to collect main lane and ramp for 7 consecutive days. For analysis that needs the FSWA approval, for example IAJRs, needs to be is recommended to have 14-day period. Traditionally we collect 2 days of data for IAJR, and several times in order to save money, even for IAJR consultant collect 1 day of data. So for IAJR, traditionally 2 days of data is collected, and several times in order to save budget and if in coordination with TxDOT, we collect 1 day of data. However, now the recommendation is for the segment data, which I believe should include main lane plus ramp, because I do not see a point of just collecting main lane segments and because if there are ramps, that would influence what is happening in between. Otherwise we will be collecting a lot of main lanes data. So I believe the segment here refers to main lane plus ramps. And IIJR 2 days, and the recommendation for IIJR is to collect 14 days of data. Now to collect 2 days, 1 day of data, we need 20 to 30,000, and this would be a sharp increase in budget. And we have to see how this plays out in future. This is a good sharp increase in budget requirements. We have to see how this plays out. We had trouble getting funding for even collecting 2 days of data. Now the requirements are to collect 14 days of data. We will see how the budget and contract plays out to follow these guidelines. But it's kind of a good recommendation, because several times there is quite a variation between typical day to weekend, and we need to capture those variations. So the guideline in itself from theoretical perspective is very good to collect 14 days of count. However, we still needs to be seen how practical it will be given the limited budget we get on projects. Suggested segment traffic data collection method is 15-minute increment, typical week, 7 consecutive days, and for IIJRs 14 days. So for typical project, 7 days segment data and 14 days for IIJRs is based on the, I believe based on the reading, the segment needs to include main lanes plus ramps. However, based on the cost it takes to collect this data, the segment might only refer to main lane here and skip the ramps. But I do not see much use of collecting main lane data just at few locations. I mean, there are some use, but not much, unless we collect the ramp data as well. So it still needs to be seen and how this will play out in terms of budget constraints. Classification counts. We typically collect classification at certain locations, typically for a day or two. The recommendation has always been to collect 2 days of counts, and again to say and because of budget constraint we end up collecting 1 day of data. Now the recommendation is to collect 7 days of class count, and for a specific period greater than 24 hours but less than a year. So recommendation is to collect 15-minute interval, typical week, minimum of 7 consecutive days for FSWA project, and minimum of 2 days for other project. So now the recommendation is 7 days for IIJRs and 2 days for typical project, and we will see how this plays out. It's not that bad as segment count. So 2 days for typical projects and 2 days 7 days for IIJR may be doable. 2 days has always been in recommendation, but because of budget constraints we have seen 1 day of data collections. So we'll see whether 1 day changes to 2 days, and for IIJR 2 days changes to 7 days. So typically for several projects, traditionally we have 1 day of class count and 2 days for IIJR. Now the recommendation is to collect 2 days for typical project and 7 days for IIJR. Oversaturated count. This is an important discussion about the difference between traffic counts and traffic demand. So if you want to know the difference between traffic count and traffic demand, please refer to one of our video, traffic, not volume demand. Please refer to one of our video in chapter 2 of the series Fundamentals of Traffic Operations. Fundamentals of Traffic Operations. This oversaturated counts, I believe this one applies to queue, which is the next one. So oversaturated counts occurs when demand exceeds the capacity. So these counts result in significant drop in speed flow through a point segment depending on the severity of congestion. So Highway Capacity Manual defines the conditions as oversaturated when any of the following are satisfied. Condition 1, if the arrival flow exceeds the capacity, then it's an oversaturation. Second one, when queue is created from a prior bottleneck of a facility that has not been dissipated yet. The second one is, let's say the peak hour has ended. Let's say we are looking at 6 p.m. and it's kind of end of the peak hour, but the queue has not fully dissipated from the peak hour itself. So it is slowly fading away, but has not fully fade away. That's also a oversaturated condition. And third one is traffic flow is affected by downstream conditions. So if there are some incident here that is affecting traffic flow, that's also an oversaturated conditions. For uninterrupted flow, oversaturated conditions result from a bottleneck on the facility. During oversaturated conditions, queue extend upstream from the point of bottleneck. So in the freeway, if there is a bottleneck here, then the queue start forming upstream of it. So if the direction of flow is like this, then this is called downstream and this is called upstream. It is recommended that traffic count collected for saturated conditions span a time interval greater than just peak hour and peak period. That's another important aspect. So we have discussed in chapter 2 that, let's say this is our volume profile and this is not a good example. Let's say this is our volume profile during AM and PM peak. So we have volume going up during AM and then going up during PM, and let's say this is our peak time. Then we should extend our data collection a little bit beyond peak time. Usually we collect 24-hour data, so we already have this, but for operational analysis it's better to start with unsaturated condition and end at unsaturated condition. So in field of traffic operations, it's better to start and end in unsaturated conditions. Unsaturated conditions means the demand is met by capacity, and vehicles are under is similar to free flow on the freeways conditions. Not free flow, but they are moving without much friction from other vehicles, and basically unsaturated conditions is volume by capacity less than 1. When they are moving at, I would say, within 60% of the speed limit. So if it is recommended that traffic count collected for oversaturated conditions span a time interval greater than just peak hour or peak period. It is suggested that field observation are conducted along with traffic segment count to determine overall peak hour and the soldering effect of traffic queue buildup or dissipation. So usually a field visit is not collected, but we do use Google Maps to see. Google Maps can give us typical traffic as well as live traffic. We use Google Maps to see when the queue is forming and when it's dissipating. Soldering effect occurs during a peak hour when a facility is oversaturated and cannot process any additional demands. In addition to traffic count, it is recommended that the queue data is collected for oversaturated condition depending on the type of analysis being performed. Refer to queue data, which is in next section, to calculate demand in oversaturated conditions. So now it's referring to one of the biggest challenge in traffic operations, which I just mentioned, which is traffic count collected versus traffic demand. We have a very good video lecture explaining the difference between these two and why it's called the biggest challenge, the biggest challenge to handle. And I'm very happy that this guideline goes through is kind of scratching the surface of the bigger issues, that is traffic count versus traffic demand. So recommended oversaturation collection method is 15 minutes. Typical weekday includes the soldering effect of traffic. Soldering effect is going beyond the peak hour on both sides. Begin count at a minimum 1 hour before congestion start and end minimum of 1 hour after congestion ends, and collect at least one intersection or one interchange upstream if congested study area. So we typically go one interchange up if there is congestion. So from the temporal limit, we try to go 1 hour before the congestion start and 1 hour after. So let's say 3 to 5 is peak hour, then we will start from 2 p.m. to 6 p.m. This is the minimum we will go. In terms of spatial limit, if the bottleneck is in this area, we typically try to go one intersection or interchange up on one intersection and interchange up from the congestion, so that the end of the project limit as much as possible lies in uncongested as much as possible. Queue data. Queue data is what we are trying to get. So queue data is recommended for oversaturated conditions. There are several ways of calculating queue data. Typically we get it from Google Maps. Another good source of getting queue data is to collect the data upstream and downstream. So let's say vehicles are under free flow here, it's called arrival rate, and there is a bottleneck, and then we know the departure rate. So arrival volume, departure volume, or arrival rate, departure rate, and the difference between these two, assuming that we account for ramps and everything, will give us the queue on the freeway. So that's how we can gather the queue data. This queue brings up an important issue of demand versus count. This is kind of scratching a surface of a bigger problem of how the counts are misleading. So for congested system, counts are misleading. Actually, when we are designing our facility, we are trying to design our facility for traffic demand, or what is the demand for the use of facility during certain hours. However, the only thing we can collect is traffic count, which is typically not equal to demand during congestions. So one good example would be, let's say we have an intersection and there are queues here. So let's say queue is extended up to here, and So the demand at intersection is pretty high, but when we go and collect the data, we may be only able to capture the data which were able to pass through this particular point. So let's say for this approach we have 200 vehicles per hour. However, the demand may be 600 because remaining vehicles are stuck in the queue and they are not able to get processed during that hour. So that's that scratching the surface of issue. This is not the complete issue of um, traffic demand versus traffic count, but I'm very happy that somebody has thought this through in the manual. So this has not been traditional focus point of the difference between demand and count. Traditionally, in 99% of cases, we go and collect the data and we use it. Collect the data and we use the data directly in the models. However, when we are working with oversaturated conditions, then we need to be more careful. All this discussion and beyond has been discussed in chapter 2 of our video series under fundamentals of traffic operations. If you want to learn more about what are these issues, how we can tackle these issues, or to understand more about why this is considered one of the biggest problem in traffic operations is traffic count versus traffic demand, please refer to this is just one of the consideration which is mentioned here, where queue is forming that masks the actual demand, and the counts are lower. But under oversaturated conditions, some counts can be higher than demand as well. It's not only on the lower side. So all those phenomena are discussed in greater detail with examples and drawings in chapter fundamental of traffic operation series. Please refer to that. I think this is a good stopping point for our discussion, and we will continue this discussion in the next video about the data. As I mentioned, if you want to learn more about the how to handle traffic count versus demand, understand more, which is one of the crucial aspect in traffic operations, however is not dealt properly. Traffic demand, the difference of traffic count versus traffic demand, how to handle these things. Is traffic count always lower or higher than traffic demand, and what causes the difference? So all these things are discussed in chapter 2 in our video series. Please refer to that chapter. It's a very interesting discussion from the perspective of traffic operations, and we will continue this discussion in the next video. Thank you.